In this video, I'm going to go through the OCR AS-level chemistry paper. This is paper 1. It's the 2019 paper, and this is the second half of the paper. I did the first half in an earlier video. So starting off here with question 22 about titration. Okay, a student carries out titration. Okay, so he gets sodium carbonate solution in the conical flask and hydrochloric acid in the burette. Okay. He makes up a standard solution of sodium carbonate of that concentration. And he puts 25 centimeters of the sodium carbonate into the conical flask. Right, the student's burette readings are shown in the table. And right, so we've got to work out the titer there. So that one is 24.20. That one is 23.85. And this one is going to be 24.30. Okay, complete the table, and we've got to work out the average titer, the mean titer. Okay, so we need to realize that we don't use that one because it isn't concordant. So we're going to just use those two. And the mean titer there is going to be obviously 24.25 centimeters cubed. Right, now from that we've got to calculate the concentration of the hydrochloric acid. Okay, so you read the question, it says we are going to have in the conical flask here, we've got 25 centimeters cubed of sodium carbonate, and the concentration of the sodium carbonate, they tell us it was I think it's 0.15, just scroll up. 0.15 mole per decimeter cubed, yeah, okay. And we're going to have our hydrochloric acid in the burette here, unknown concentration. The average titer, we've just worked that out, that was 24.25 centimeters cubed. That's our hydrochloric acid. And if you look at the equation, we can see it's a 2-to-1 ratio, so it's 2 moles of HCl to 1 mole of sodium carbonate. Right, so the first thing to do here is to work out the moles of sodium carbonate in the conical flask there. So moles Na2CO3 is equal to the concentration multiplied by the volume. The concentration is 0.15 moles per decimeter cubed. The volume, 25 centimeters cubed, so that's 25 over 1,000. That gives us 3.75 times 10 to the minus 3 moles of sodium carbonate. Now, as we just said, it's a 2-to-1, 2 moles of hydrochloric acid to 1 mole of sodium carbonate. So therefore, the moles of HCl in the titer is going to be that multiplied by 2, which gives us 7.5 times 10 to the minus 3 moles. Okay, that's our moles of HCl. Now we know that that was in a volume of that, so let's work out the concentration of HCl. Is equal to the moles over the volume. So that's 7.5 times 10 to the minus 3 divided by the titer, 24.25 over 1,000. That gives us 0.30927. moles per, okay, but it does tell us to give it to 3 significant figures. So that's going to be 0.309 mole per decimeter cubed is our final answer there. It's a pretty straightforward titration because they're not really asking you to work out like water crystallization or anything. It's just finding out the concentration. So even for AF, a little bit on the easy side, that one. Okay. In the titrations, the student measured the volumes with the pipette and the burette. The pipette gives you the uncertainty, burette gives you the uncertainty. Determine whether the volume measured by pipette or the burette has the greatest percentage uncertainty. So let's do the pipette first. Okay, so percentage uncertainty is for the pipette is going to be the uncertainty 0.04 over the volume you used to measure 25 multiplied by 100. That's going to give us a very low percentage error. 0.16%. Right, now let's do it for the burette. Now we have to be careful with the burette because each reading's got an uncertainty of 0.05. And we take 2 readings, the initial and the final. So we've got to multiply by that uncertainty by 2, which gives us 0.1 centimeters cubed. And the titer there was 24.25 centimeters cubed. But let's do the smallest titer, which gives us the biggest uncertainty. Well, that was 24.2 centimeters cubed. So percentage uncertainty for the burette is going to be bigger than that, I'm pretty sure, but you should probably show the calculation because it is 2 marks. So that's going to be that 2 times 0.05, 0.1 over 24.2 multiplied by 100. That gives us 4.41%. Okay. So it's quite a lot more. That's 0.41. The burette is bigger, 3 times bigger, the error really, than the error for the pipette. Okay, question about halogens and halides. The boiling points of the halogens are shown in the table. Explain the trend in the boiling point of the halogens. Right, this I think is a 3-mark question. It's 3 marks. Okay, so I think to be on the safe side, just state the boiling point. The boiling point increases as you go down the group. Right, why is that? Well, I think probably worthwhile stating all exist as diatomic molecules. So you're not going to get any permanent dipoles. You're obviously not going to get hydrogen bonding as the intermolecular force. So the only intermolecular force you're going to get are London forces. And I think you need to say these get bigger as the molecules get bigger. Got more electrons and more points of contact. And it's always worth mentioning, if you look at the mark schemes, they always seem to give a mark for saying, yeah, stronger intermolecular forces, that means you need more energy to break those intermolecular forces. So you need a higher temperature. Boiling temperature is higher. And be really careful then not to even ever suggest that you're breaking the covalent bonds between the halogens when you boil them. When you're not, obviously, you're just breaking intermolecular forces. Okay, you're supplied with a sample of ammonium bromide. Describe simple tests to identify the cation, where the cation is the positive ion, which is ammonium, NH4+, and the anion, which is Br-. Okay, and include reagents, observations, and relevant equations, sorry. Right, bromine then, let's do that one first. So you test for bromide ions, you add acidified silver nitrate. And if you've got bromide ion present, you'll get a cream precipitate. And the equation you want there is you've got Ag plus ions in aqueous solution from the silver nitrate bromide ions in aqueous solution, and you're going to get AgBr solid, which is a cream precipitate. Maybe worth mentioning that this will only dissolve in concentrated ammonia. Silver iodide, which looks similar to cream, but it looks yellow really, that won't dissolve in conc ammonia. So if you do that test with ammonia, sometimes to avoid that ambiguity, may or may not be necessary. If you look in the mark scheme, that second part. Now we need to know how to test for the ammonium ions. Well, the ammonium ions, you turn into ammonia gas by adding some by adding some sodium hydroxide solution. I'll just draw it as an ionic equation. What that will do is the OH minus is a good base. It will remove a proton from NH4 plus. So you'll form NH3 gas and H2O. Okay, so it is best also to warm that to make that sure that reaction has happened. You warm it. And then you test for the presence of NH3 gas by using damp red litmus. The ammonia will dissolve in it and turn it blue, because ammonia, when dissolves in water, forms an alkaline solution. So you hold the red litmus above the surface of the liquid. Obviously you don't put it in the liquid because it would go blue anyway then, because you've got sodium hydroxide in there. You hold it above the surface. Okay, so a lot of those marks going for the equations, 5 marks there. Right, ammonia is made from nitrogen and hydrogen and a reversible reaction. Okay, so you got the reaction there. Explain how Le Chatelier's principle can be used to predict the conditions of temperature and pressure for a maximum equilibrium yield of ammonia. Okay, so it's not asking about operating conditions here and compromises. So the question clearly states it's just the conditions you want for a good equilibrium yield. So don't go into that bit, you're wasting time. Right, so let's think about temperature. Right, we look at this, the temperature, this is an exothermic reaction. So we should use a low temperature. Le Chatelier tells us that that will move the equilibrium. In the exo direction, you'll try and warm it up if you cool it down. In other words, it will move it in the forward direction. You'll get more ammonia produced. Right, now we need to think about pressure. So the pressure, we have got 1 plus 3. We've got 4 gas moles on the left and only 2 gas moles on the right. So that means we want to use high pressure, increase the pressure. And Le Chatelier tells us that will push the equilibrium to the side with the fewest gas moles. And worthwhile stating, we've got 4 on the left and only 2 gas moles on the right. Okay, a few 4 marks there. That is all you need to say. Right, now we've got to work out the value of the equilibrium concentration. So they've given us the equilibrium, so we've got to work out the value of the equilibrium constant, sorry, Kc. They give us the equilibrium concentrations. So we need to write down the expression for Kc, which is the products, and it's going to be ammonia concentration squared divided by the reactants, which is hydrogen concentration cubed, multiplied by nitrogen concentration to the power of 1. Okay, and let's put the numbers in there. So they do give us the equilibrium concentrations. They don't give us the equilibrium moles here, so we don't need to worry about that. So this is going to be 0.862 squared divided by 2.75 cubed multiplied by 1.25. And if we do that, right, once it in standard form, significant figures, so we've got Right, we do that, we get 0.028589. Now that's not in standard form, and it's not the correct number of significant figures. It should be to 3 significant figures. So we change that to standard form. We get 2.86. That becomes a 6, of course, multiplied by 10 to the minus 3. It doesn't actually ask us for units, but the units will be mole to the minus 2 dm to the 6. Okay. Right, ammonia is used to make nitric acid. The first stage of the reaction is shown below. Okay, and they give us delta H for that reaction there. Standard enthalpy changes of formation are given in the table. State the conditions of temperature and pressure used for standard enthalpy measurements. Right, the temperature is 298 Kelvin, and the pressure is 100,000 pascals, 100 kilopascals. That's just straightforward recall. Now we've got to calculate the standard enthalpy change of formation for NO. So they give us the enthalpy of formations for all the other reactants and products, and they give us delta H for the. So we've got to, which energy cycle do we use? We're going to use Hess's law, right? We're obviously, well, if we're given delta HF data, what's the third thing we always put down here? Is that elements in the standard state. So that's going to be 2 nitrogen molecules, and we're going to have 6 H2 gas and 5 O2. Now it's formation. We are forming these things from the elements in the standard state, so the arrows are going to go up. Okay, so I'm going to draw the arrows going up. Right, and it tells us the value of delta H. I'm drawing that line. They tell us it is minus, there it is, minus 908 kilojoules per mole. So I'm going to write that there. Okay, and now we need these values, delta HF values. Right, ammonia. Right, I'm going to copy that table. I think I can't see it there. Okay, so we've got those values there. Right, now on the green arrow, we're forming 4 moles of ammonia, so that's going to be 4 times, sorry, do it in green, 4 times minus 46. And we're forming, well, nothing happens to the oxygen, so we just ignore that. So let's add that lot up together. 4 times minus 46 is minus 184. On the red arrow, we're forming 4 moles of NO. Now that's what we've got to find out, NO. So let's call that X. So it's going to be 4X. Okay, minus 4X. Okay, sorry, not minus 4X, just 4X. And what's the enthalpy of formation of water, gas, is 242. So that's going to be plus minus 6 times minus 242. So add that lot up together. We get 1,452 plus 4x. Okay. Now we're going to use Hess's law. So we know that this number here, this here, we're going from left to right, minus 908. Minus 908 is equal to, now we're going against the green arrow, so we change that minus 184 to plus 184. We're going with the red arrow, so we keep the sign, so it's minus 1452 plus 4x. Right, let's do a little bit of rearrangement there. So we're going to get minus 908, doing black, sorry. Minus 908 minus 184 plus 1452 is equal to 4x. Do that in a calculator. And I wouldn't do it all on your calculator. I'd write down steps like this in case you make an intermediate error, and then you're not going to lose all the marks. That's equal to 360 is equal to 4x. So x is equal to 360 divided by 4. That's 90. I'm going to give that, just to remind myself that it's plus there. What were we asked to find out? We were asked to find out the delta HF of NO, which is equal to x. So that is equal to 90 kilojoules per mole. Now it said give it to the nearest whole number. Well, 90 is a whole number, so we can just leave that. And I would put a plus in there. And it's quite unusual for things to have a positive enthalpy of formation. Usually compounds have a negative, not always, but usually they do. Okay. On some organic chemistry, the question is about alcohols and alkanes. 3 alcohols have the structural formula C4H10O. Each alcohol is refluxed with the acidified dichromate, which will of course oxidize. We will oxidize them. Okay, and if you reflux, you get, like, remember, if you oxidize a primary alcohol, at first you will get an aldehyde. But if you reflux it, you're going to oxidize it all the way to a carboxylic acid. Okay, so then we need to remember that. Now, if there's no organic product, write none. Let's think about this first alcohol, A. What kind of an alcohol is it? Well, there's the carbon to which the oxygen is attached, and it is only attached to one other carbon. So that is a primary. So that's going to go to a carboxylic acid. So let's draw that. So the carbon skeleton doesn't change, of course. Okay, with that red carbon there, I'll do it in red. That's where the oxidation occurs. So you're going to get a double bond O and an OH there. Let's turn into a carboxylic acid. Right, let's look at B. B, the carbon to which the alcohol is attached to the red one is attached to 3 others. Now that means it is a tertiary tertiary alcohol, so it can't be oxidized, so you won't get any product there. None, no product. The next one, you can guess it's going to be a secondary really, but let's just check. So the carbon to which the OH is attached is that one, and that's attached to 2 others, that one and that one, so it's a secondary, so that's going to be oxidized to a ketone. So we keep the carbon skeleton the same, but that alcohol gets oxidized to a ketone. Okay, that is the products, that's the answer to that. Right, the systematic name for alcohol C. I like to number it. So let's look at the longest carbon chain. It's going to be 1, 2, 3, 4. So it's going to be butanol. And because this is the OH is on number 2, it's going to be butan-2-ol. And just be careful not to name it obviously the other way around, like 1, 2, 3, 4. You wouldn't be correct to call it butan-3-ol. You always use the smallest number. Right, the equation below for the complete combustion of alcohol A. Complete combustion means you're going to get carbon dioxide and water as the product. So you're going to get CO2 and H2O. Well, we've got 4 carbons in the reactant. So 4 carbons, 4 CO2s we're going to make. We've got 10 hydrogens there, so we're going to make 5 O2s. So how many oxygens on the right-hand side? We've got 4 times 2 in the carbon dioxide is equal to 8, plus 5 there, which is going to make 13 oxygens. So how many O2 molecules are we going to need? Well, we've got 1 oxygen in there already, so we don't need 13, we only need 12. So it's going to be 6 O2. Right, okay, this is about free radical substitution. Right, under suitable conditions, butane reacts with chlorine by radical substitution. A mixture of organic compounds is formed, including C4H9Cl and compounds D and E. Now, compounds D and E, we've only swapped 1 hydrogen for a chlorine in that one. D and E, you're going to get more, okay, presumably. Complete the table below to show the mechanism for the initiation and propagation stages. Okay, right, initiation. You always get the chlorine molecule breaking up to form the two free radicals. So that's Cl dot, and there's going to be two of those. And the conditions you need for that are obviously going to be UV light. Okay. Now propagation. Okay, the chlorine free radical, I'll write it down at the bottom to give me a bit more space. Right, chlorine is then going to react. This is fairly, okay, the chlorine free radical is going to react with the butane molecule. We can use molecular formula here, so we don't need to draw structures. It's going to remove one hydrogen from that to form HCl. And in doing so, the hydrogen comes off with its electron, so it leaves behind a free radical, an unpaired electron. That electron dot there was in the bond between the carbon and the hydrogen. The hydrogen has gone away with its electron, so it's a free radical. That's propagation. Now that free radical then reacts again. It's very reactive. It's going to try and pair its electron up by reacting with a chlorine molecule. It removes a chlorine to form C4H9Cl and leaves behind a chlorine free radical. So propagation, and essentially the chlorine free radical has behaved as a catalyst. It's been used up, then it's been regenerated, and you can have multiple cycles of that. So that's the reaction there. Okay, compound D is formed by the substitution of all the H atoms in the butane atoms. Use the equation for the formation. Write the equation for the formation of compound D. So butane is C4H10, and we're going to replace every single hydrogen there. So we're going to get C4Cl10, and those hydrogens all pair up with a chlorine to form hydrogen chloride. And there's 10 of them, so we need 10 HCl there. So we've got 20 chlorines on the right hand side, so that means we need to have 10 Cl2 molecules on the left. The main mistake people make here is they always forget that you form hydrogen chloride as the byproduct. You don't get hydrogen gas or hydrogen free radicals or anything. It's hydrogen chloride or hydrogen bromide if you use another one. Okay, right. Compound D, which is multiply substituted, is so you've substituted some of the hydrogen atoms, but they're not going to tell you how many. Okay, now, so how we're going to do this, we are going to find out, we need to work out the molecular formula of compound D. To do that, we need to first work out its molecular weight, its MR, its molar mass. And how are we going to do that? We're going to use, we're using gas volume. Okay, so moles, the moles of E is going to be the volume in centimeters cubed over 24,000, which is 78 over 24,000. That is equal to 3.25 times 10 to the minus 3. Okay, so that's how many moles of E we've got. Right. Now we know that it had a mass of, this many moles had a mass of 0.636 grams. And we know that moles is equal to mass over MR. We want to find out the MR, so let's rearrange that. MR is equal to mass divided by moles, which is equal to, the mass is 0.636 divided by 3, the moles, 3.25 times 10 to the minus 3. That's equal to 195.7 okay. Okay, 195.7 is the MR. Now, we've got to think how many chlorine atoms are in that. Okay, now it came from butane. Butane is C4H10, and the MR of that is 58. Right, so this is obviously a lot heavier because it's got some chlorines in there. Well, how many chlorines? Let's see. So let's do 195.7 minus 58, and that's going to be approximately equal to the weight of the chlorine. Not exactly, because there's a few hydrogens going to go there. That gives us 137.6. So how many number of chlorine atoms then? Well, chlorine has got an atomic mass of 35.5. So let's divide this number 137 by 135.5. Do that. 137.6 divided by 35.5 is equal to 3.87. Okay, 3.87 chlorine atoms. So let's try it with 3 chlorine atoms and see how that works. Okay, so we're going to get what would be the MR of that molecule? We're going to get that would be C4, and it won't be H10, it would be H7, because we're going to replace 3 chlorine atoms, Cl. Well, the MR of that is equal to 48 for the carbons plus 7. Sorry, that should be a 3 there. Right, that's 161. So that's too small. So let's just try C4H6Cl4. That's going to be, what's that going to be? 48 plus 6 plus 4 times 35.5, 196. Okay, 196, which is pretty close to this number here. So we can safely say we've got 4 chlorine atoms substituted there. So the molecular formula of the substance is that. We don't know where those chlorines are. They're all on the same carbon or different carbons, but that is the molecular formulae, and that's what it's asked us to do. And that is the end of the paper.